This next section, 40.5, deals with the atomic spectra and the equations that we're able to derive because of Bohr's postulate. Remember, Bohr does not understand why angular momentum has to be quantized, as we previously had, and he had said that the angular momentum for an atom for the nth orbit, for an electron in the nth orbit, must be that integer n times Planck's constant divided by 2 pi, where n is equal to 1, 2, 3, or some integer. And this is where we get the idea of quantum theory, that something cannot be continuous. Like in classical mechanics, angular momentum is continuous. Here it is not. It has to be discrete. Well, there was a discovery made about these lines in atoms. And the discovery was that, and it's just hard to believe that these various scientists discovered these series, the Lehman series, the Balmer series, the Paschen series. It was discovered that 1 over the wavelength of the light that's emitted from an atom is a special constant, r, times 1 over one integer squared minus 1 over another integer squared. Now, who on earth could have discovered something like that? If someone gives you the frequencies of all the emissions for different types of atoms, and you would not say, oh, I believe the reciprocal of the wavelength is proportional to the difference of the reciprocal frequencies of the squares of two integers. How someone figured that out is totally beyond me. However, we can say this was discovered not theoretically but experimentally. It's an experimental result. This is the theoretical result that Bohr had that actually implied the quantization of atoms. Now what we're going to do is we're going to take this and see what we know about atoms and how they behave. Well, if we have a nucleus and we have an electron going around it, then we know that we have to balance two forces. The centripetal force to push outward and the attractive force to pull inward have to be equal. Well, that's given by this equation right here. So we can say that mass times the centripetal acceleration, which is v squared over r. You recall we had that from the last chapter. Mass times centripetal acceleration, m, acceleration centripetal, is mv squared over r. That's the force pushing outward. And the force pulling inward is, of course, the electrical attraction. Since this is positive and the electron is negative, we have an attraction, and the attraction by Coulomb's law is going to be equal to the force, which is K, which is 9 times 10 to the 9th, you recall, from electricity, times the number of electrons here, which we're going to call Z, that's the atomic number of the nucleus, times E, that's the total electronic charge in terms of protons in the nucleus, is Z times E, because I've got this many charges, and each one has a charge of E, times the charge on the electron, which is E, so that gives me a ZE squared, and it's a 1 over r squared force, so I have a 1 over r squared here. So this equation must hold. Now, in the past, we knew that we must have the centripetal force and the Coulomb force balancing each other. But if you look at this equation, then you notice that r occurs in it in the velocity, but you can have any r in any velocity as long as they obey this equation. That gives us continuous orbits. Now we have, however, another equation, that of Bohr. And so now you have two equations in two unknowns, and we can get a definite answer on what orbits are allowed. So we can come back to this equation and look at it, and we get mv squared over r is equal to k z e squared over r squared. And of course, this r here is going to cancel with one of the r's here. And you can solve this for r, the r that remains, by putting it over here. And I could actually change that to the momentum by putting another m here. And I'll show you how that goes. Take the r and bring it to this side, so I would then have r is equal to kz e squared over mv squared. But I could multiply the numerator and the denominator by m, and that would give me m squared v squared, which is p squared. So r would be equal to p squared divided into kz m e squared, where I've added this mass because I squared this mass down here, and you recall that p is equal to mv. So this shows us what the radius has to be. But p times r is going to give us the angular momentum. So L is going to be equal to r times p, and this is the p perpendicular, and that's got to be equal to n times h bar. So what do I have here? I have two equations for two continuous variables, r and p, and another equation for r and p. And if I look at them, of course, this can be any integer. This is fixed, this Planck's constant. This k is fixed, 9 times 10 to the 9th. Z is the number of protons in the nucleus. The mass is fixed. The charge is fixed. So there are no other variables in this equation. And if we solve that, one can show the following. I'm not going to go through all of this algebra, but the equation is right here. The radius of the nth orbit is going to be equal to h squared over n squared. I don't have the, let's see, the 2 pi. There is a 2 pi right here. I've written it as 4 pi squared. That'd be 2 pi into the first h. So we can say h bar squared, n squared, divided by km e squared z. Km e squared z. And this is equal to, if you work out all of these constants, 5.29 e to the minus 11th times n squared, which is any integer, divided by z. And this gives us the nth orbit. So n can be 1. It can't be 0 because this would give us a radius of 0. And so n can be 1, 2, 3, and if z is equal to 1, like for the hydrogen atom, there's only one proton in the nucleus, so we can forget the z and would say, okay, for the lowest level, n would be 1. The next level, n would be 2, so we get 2 squared here, and so forth, and that would give us the radius of the orbits. And this equation right here, of course, is incredibly important. And we can not only determine this, but we can also look at the energy. You recall the energy is equal to the kinetic energy plus the potential energy, which is 1/2 mv squared for the kinetic minus the loss of kinetic energy, which is kz e squared over r. Remember, it's a 1 over r, not 1 over r squared. And this gives us our energy. Well, now, this is the value r and the value p. We know exactly what those can be for the different orbits. I'm not, again, going to go through the algebra, but one can show the following. Let me move this paper up a little. And one can determine it from this equation right here, that the nth electronic orbit is 2 pi squared m k squared e to the 4th over h squared, that's not h bar now, times z squared over n squared. It takes some doing to plug these things in and determine what this is, but for the nth orbit, the radius is going to be this, and the momentum can be determined in terms of that from this equation. And so what we get as a result, just from some simple 9th or 10th grade algebra, we get the nth energy level is equal to minus 13.6 electron volts times Z squared over N squared. Electron volt is a unit of energy rather than using the joule. This is the energy that one electron has dropping through a voltage difference of 1 volt. And for a hydrogen atom, if I look at N is equal to 1 here and Z is equal to 1, then in fact you see that the lowest energy level of the hydrogen atom is something you should remember, is 13.6 electron volts. And it's negative because it takes this much energy to take that electron all the way out to infinity, basically to ionize the atom. So this is called the ionization energy for hydrogen from the lowest energy level. Now we have all of the energy levels, and they are this number for a given atom, like whatever Z is for that atom. I just look at N squared, and it's 1 over N squared for all the different levels. And so I can predict what the energy is for each of the levels. Once I can predict the energy, then I can do something really incredible. If an electron drops from one energy level to another one, then I can look at the change in energy, and the change in energy must be equal to h times the frequency. By Einstein's original equation, and therefore this gives us the frequency of light, and likewise one can then rederive this equation for the wavelength of the light and actually derive this constant and prove that it's 1 over the N squared between the two orbits. Now again, I've got here in the notes, note that the factor 13.6 electron volts is the ionization energy of hydrogen. And if I compute 1 over the lambda, which is the frequency divided by c, that's because wavelength times frequency is always the speed of light. I can look at what 1 over the wavelength is. It's going to be the frequency over c. Then I can actually compute what that 1 over wavelength is, and you notice I get a whole bunch of constants. It looks kind of messy, and then I have a 1 over N squared. So except for those constants, I get all this junk and then a 1 over N squared, and that exactly predicts this equation that we had back up here, where 1 over lambda is equal to R times 1 over N squared for the first level and 1 over N squared for the second level. And we have a theoretical prediction of that. This is a remarkable result here, and it really involves no more than some kind of messy algebra at the high school level. The takeaway points here to remember are: the energy is a constant, the ionization energy in electron volts over N squared. The radii, this gives us the radius of each of these, and I should point out something about this radius. If I look at the diameter of the atom, it's about twice the radius, which is about the diameter of hydrogen, which would be Z is equal to 1 and N is equal to 1. It would be, the diameter of hydrogen would be about 5 and 5's 10, or e to the minus 10th, not e to the minus 11th. And this is 1 angstrom. E to the minus 10th meters is 1 angstrom. And that tells us that the hydrogen atom is about an angstrom across, or 10 to the minus 10th meters. And that comes directly from this equation here.